I'm Bojong, and today I will talk about our work on transit analytics. And this is a joint work with my colleague Lei and with my advisor Suman Banerjee. So public transportation serves millions of people every year. And this graph shows the annual ridership of a fixed route in Madison, Wisconsin from year 1970 to year 2014. And this year is year 1989, the year I was born. And it has 9 million boardings. But I don't know what happened before I was born. But after that, you can see a clearly rising trend of the boardings. And in year 2014, it has more than 15 million boardings. So the transit operators, in order to provide a better service, the transit operator may ask questions like, shall we start a new route from place A to place B? Or shall we adjust the transit schedules to serve more people, especially in the rush hours? So to answer these questions, transit operators need passenger usage information. And they are very interested in the information like what's the population, origin, destination pairs in a route, or what's the occupancy of the vehicle at different times of the day, and what's the average waiting time for a person to get on the bus, especially in the rush hours. So here comes the question, how can the transit operators get this kind of usage information? So they already put a lot of effort into it, and even today, they may take surveys. They may ask volunteers to take surveys and get feedback from them. Obviously, this kind of approach needs a lot of human labor work and is very inefficient. So a smarter way may be using the ticketing system to keep track of the passengers. However, if you want to use the tickets, you may only know when and where the passenger gets on the bus, but you may not know when and where the passenger gets off the bus, at least for most ticketing system in US. And if they're paying cash to buy the tickets, and you may lose track of them. And camera is also another solution, but this is a costly solution in both hardware and software. And it may not work during night times, and it also may generate privacy concerns. So now I will introduce our solution. We call it Trellis. And the key challenge for our approach is that how do we determine an individual is inside the bus or outside the bus? And given the fact that almost everyone has a smartphone today, and more and more bus transit starts providing the Wi-Fi accesses, and our system trying to leverage the widely available smartphones with the Wi-Fi systems on board, and we proposed a Wi-Fi-based monitoring system that can keep track of the passengers by tracking their smartphones. And all we need is a sniffing module on board and a GPS module to keep track of the location the bus traveled. So as I mentioned before, the key challenge is to determine whether an individual is inside the bus or outside the bus. And as previous talks mentioned, a lot of existing indoor localization techniques have been developed, and they usually use the received signal strength indicator and combine with some complicated mathematical model to solve this issue. But our solution uses a much simpler mechanism to solve this issue. Suppose a passenger is sitting in the bus, and we have a pedestrian walking along the street, and they both have smartphones with their hand, and the smartphones can send out Wi-Fi signals. And it also has the onboard Wi-Fi access point. And here's the red circle means the service range of the access point. And initially, both of them right now are within the service range. But when the vehicle moves, we can see that eventually the pedestrian will out of the service range. So what we can observe from a vehicle-mounted observer is shown in this graph. And the left axis is the speed, and the right axis is the RSSI level, and the x-axis shows the time in seconds. So the blue lines are the received signal strings from a passenger's device, and while the red dots are the signal strings received from the pedestrian's device. Vehicle moves, and the pedestrian the passenger signal strings will fluctuate and eventually disappear. And based on this observation, our system can easily tell whether an individual is a passenger or a pedestrian. So we implement our system on a specialized Wi-Fi gateway, and we have deployed the system into 2 city buses in Madison, Wisconsin. And we use one thread to collect the Wi-Fi package data, and one thread to collect GPS location information, and another thread to send the collected data to a data analysis module for real-time analysis. So here's an overview of the hardware we used. In the middle is a wire rover gateway box. For more information about wire rover, you can read our paper and for more information. And it comes with a 4G cellular card and a Wi-Fi card, also a GPS. And we put this hardware on those 2 city buses. And this map shows the overview of the bus route. And it usually takes 45 minutes to 50 minutes for a round trip. And it has 46 stops along the road. For easier analysis, we divided this into 7 regions. And as shown on the map, Region 1 is a residential area. It's where the university apartments for graduate students located. And Region 3 to Region 7 are the main campus area. So we have recorded data from those 2 city buses for around 90 days, 12 hours per day. And basically, the bus may come online in the morning and go back home in the afternoon. And the total distance travels for those 2 buses are more than 10,000 miles. And we have identified more than 114,000 devices from the data we collected. And next, we will evaluate our Trellis approach by 2 example applications. One is passenger tracking, and the other one is transit analytics. So since you already know our approach can clearly determine an individual is a passenger or a pedestrian, the next question is that how can we know for a passenger when and where does he or she get on or off the bus? So this, I will use this picture to show you how we do that. And the left axis, again, is the speed of the vehicle, and the right axis shows the RSSI value of the received packets. And the blue line is the vehicle speed, and the red dots are the received packets from a device. And in the beginning, as you can tell from the vehicle speed, the vehicle is stopped at some bus station, and we see an increasing of the RSSI value, and then it stays stable for a while, and then we can know the passenger is getting on the bus, as shown on the map. And then at some point, the RSS value starts to drop, and we can also see from the vehicle speed, and it drops to 0, which means it comes to a stop and then moves away. And eventually we see the RSSI value disappear, which means the passenger left the bus. So after we can determine when and where the passenger get on and off the bus, we conduct the automatic passenger counting to record the passenger usage information. And to evaluate our counting algorithm, we calculate the correlation between the ground truth with the estimated passenger number. And to get the ground truth data, I myself jump on the bus 6 times and count the passengers stop by stop manually. And here, the x-axis shows the date of the data was collected. And the y-axis shows the passenger number. And the red dots are the ground truth data, and the blue dots are the calculated passenger number. So finally, we reach an average correlation of 0.76. And next, I will tell you about some bus stop statistics. And we summarize the average number of passengers get on and off the bus at different time during each hour and different time of a week in this graph. And you can see the x-axis shows the 7 days of the week. And for each grade, it represents the hours in that day. And the y-axis is the passenger number. And you can see clearly that there are peaks in morning hours and evening hours, which means that people are getting on the bus in the morning and a lot of people get off the bus in the evening hours. And this data is collected from a bus stop in the residential area. So this means like all the people living there go to work from their home in the morning, so they get on the bus. You can see peaks there. And then in the afternoon, they get off bus and go back home. That's why there's a peak. And here's another figure shows a bus stop in the main campus area. So in main campus area, the students will use the bus from dormitory to teaching building, or from one teaching building to another one. So you can see from the data, there's no obvious peaks, but you can see passengers getting on and off the bus throughout the day. And next, we summarize the passenger movement from region to region and during different time of day. And in this origin destination matrices. And original region means where the passenger get on the bus. And destination region means where the passenger get off the bus. And this matrix shows the morning hours from 7 a.m. to 9 p.m. And for each boxes in this matrix, the darker the color, the more passenger. And for example, we can see a lot of traffic happen from region 1 to region 3 during morning hours. As I mentioned, region 1 is the residential area, and region 3 is the main campus area. So it means that during morning hours, most people get on the bus and go to work. On the contrary, in the evening hours, from 5 p.m. to 7 p.m., and let's focus on this region, this column. It means that most traffic happens in this column means the passengers get off at region 1, which means they are going back home from work during evening hours. So in conclusion, we have proposed a low-cost Wi-Fi-based and a passive cross-sort approach that can let you infer how passengers use the transit analytics. How does the passenger use the transit systems? And for future work, we plan to first improve the device identification accuracy, like by adding more Wi-Fi monitors on the bus. And we plan to deploy more Trellis on more buses and routes. So by doing that, we can study some interchange bus stations, like study the usage of the interchange bus stations. And finally, we can evaluate other complementary techniques, such as use Bluetooth beacon to determine passenger getting on and off the bus. That's all for my works. Thank you. Ready to take questions.